Okay, so ever feel like the software you're using could crumble like a stale cookie if you look at it wrong?
Yeah, we've all been there.
Today we're diving into something that might help with that, the solid principles of software design. And these aren't just, some abstract theories.
Right.
These are like the building blocks of how to make software that's actually, strong, adaptable, and let's be honest, less of a pain for everyone involved.
Definitely. Think of solid principles as kind of like the architectural plans for clean, easy to maintain code. So just like a well-designed building, good software built on these principles can handle changes and updates without turning into a complete mess.
And our guide on this deep dive is Mason Coding and their Medium article, Los Principios Solid, Fundamentos para un Software Robusto y Mantenible. Okay, gotta ask though, an article about software design in Spanish. What's the story there?
It's actually pretty interesting. It just goes to show how these principles really are universal. They address like fundamental challenges in software development, no matter what language you're writing in. It's like the concept of delicious, whether you say delicioso or delicio, everyone understands what a good meal is, right?
I like that. So, solid principles, they're like the universal language of good software. All right, let's unpack this acronym. S, Single Responsibility Principle.
Mason Coding uses a chef analogy for this one, right?
Yeah, they do. So picture this. You have a chef, right? And they're known for just this one amazing pasta carbonara. That's it. That's their thing. They've completely focused on perfecting that one dish, and they're a master at it.
Laser focus. Exactly. That's the whole idea behind the single responsibility principle. In software, it means each piece of code, each module or class should have one job, one responsibility, and it should do it really, really well.
So instead of this massive chunk of code trying to do everything at once, you break it down into smaller, bite-sized pieces, and each one has its own clear purpose. Like almost like in a restaurant, how you have chefs for appetizers, then you have chefs for entrees, you got your pastry chefs for desserts.
Exactly. It makes the code so much easier to work with. Easier to understand, to test, to maintain. Going back to our chef, imagine if that carbonara master also had to, like, bake the bread, manage the inventory, and wait tables all at the same time.
Oh, yeah, that pasta would probably suffer.
For sure. And it's the same with code.
Right, like that saying, jack of all trades, master of none. You don't want your code to be jack of all trades, you want it to be a master. But how does this actually work in, like, real-world situations?
Okay, so let's say you're building a banking app, right? A single responsibility in that app might be like processing a user's transaction. Now, if that logic is all tangled up with the code for, let's say, displaying account balances or updating security settings, any tiny change in one area could accidentally mess up the whole transaction process.
Yeah, that's not good.
And you know what that leads to?
Frustrated customers, lost money, the whole 9 yards.
Exactly.
So the single responsibility principle, it's all about keeping things separate so you avoid those domino effects and make that code super reliable.
Exactly. And that reliability, it's better for everyone, developers, users, everybody.
Okay, S for single responsibility. Got it. On to open-close principle. What's that all about?
This principle is all about making sure your software can adapt and change without, falling apart.
It's just difficult. How do you even start with that? Making software that's ready for anything.
Okay, picture a really well-designed house, right?
Yeah.
You can add new rooms, you can renovate all without having to demolish the whole building. The open-close principle wants us to design software with that same flexibility. You want to be able to add new features without ripping apart the code you already have.
So open to adding new things, but closed to needing a major overhaul every time someone wants a new feature. Clever. How does that work in reality, though?
Okay, so let's go back to our banking app.
Right.
Let's say you want to add a new kind of account, like a student checking account.
Yeah.
With this principle in mind, you wouldn't want to go directly into the existing code that handles all the other types of accounts.
Right, because messing with code that already works, that's how you break things. You don't want someone's debit card to stop working because you added a new account type.
Exactly. So instead, you'd use this idea of inheritance and make a brand new class just for these student checking accounts. This new class, it would take all the basic stuff from the regular account class, but it would also have its own special features and rules.
So like a specialized version of something you already have without messing with the original blueprint.
Yeah, exactly. And that way, you can make the system do more without risking the stuff that's already working. Think of it like adding a new wing to your house, instead of trying to cram an extra room into a space that's already full.
I'm starting to see why these principles are so important. It's like they're like guiding principles to help you navigate the craziness of software development and actually build systems that are both, tough and adaptable.
That's it. And the best part is we're just getting started. We've got a whole bunch more to uncover, each one with its own insights into making elegant and maintainable code.
All right, I'm hooked. Let's keep going. What's the L in solid all about?
So speaking of adding new features smoothly, that brings us to L, the Liskov Substitution Principle. It's all about making sure the different parts of your code can work together peacefully, even when you swap out some of the pieces.
So like having interchangeable parts in a machine. As long as the new part fits the specs, the machine keeps running.
That's the idea. Imagine a car engine. Spark plugs, battery, you can even swap out the whole alternator, right? As long as replacements match what the car needs, the engine's happy. Doesn't care if it's the original part or a compatible one, it'll work.
Okay, I got that. But how does this principle actually work when we're talking about code?
You know how we talked about adding that student checking account to our banking app, making a new class that's based on the main account class?
Yeah.
The Liskov Substitution Principle, it makes sure that new student account class can jump right in without causing any weird problems.
Okay, so it's like our student checking account is a new player joining a basketball team. As long as they know how to play and they know their position, they should fit right in, no problem.
Yeah, exactly. The whole system shouldn't even skip a beat. It should handle transactions, interest rates, all that stuff for this new account just as easily as it does for the old ones.
Makes sense. It's like having a guarantee that any specialized component you create, it's going to play nice with the rest of the system. And that helps you avoid those code clashes that can lead to bugs and crashes.
Exactly. And this principle is super important when you're building software that needs to be, both tough and flexible. It lets developers experiment with new components without worrying about accidentally breaking something that's already working.
This reminds me of the time I tried to bake a cake with gluten-free flour. Figured I could just swap it in, no problem, right?
How'd that go?
Cake was dense, crumbly, a total disaster. It's like my gluten-free flour, it didn't follow the Liskov substitution principle, didn't act the way the recipe expected it to.
See, a perfect example of what happens when you ignore this principle. Sometimes those swaps that seem simple can have unexpected results. And with software, those results, they can be a lot worse than a ruined cake.
Yeah, definitely not the kind of critical error you want popping up in your banking app or anything. Okay, L for Liskov substitution, check. What about I in solid? What's interface segregation all about?
All right, so if we're sticking with our food analogies, think of the interface segregation principle as the art of creating the perfect menu.
Yeah.
You want something that appeals to everyone's tastes without overwhelming them with a million different choices.
Yeah. Okay, so instead of one of those huge menus with a million items on it, we're talking smaller, more focused menus, like a separate menu for appetizers, entrees, desserts, that kind of thing.
Exactly. It's about making things more organized and easier to digest. You don't want people to feel overwhelmed or accidentally order a side dish when they meant to order an entree, right?
Right. And it's probably way easier on the kitchen staff if they can focus on making a specific type of dish instead of having to know how to cook everything on a massive menu.
Exactly. Now let's take that same idea and apply it to software design. Instead of having one massive interface that every single piece of code needs to talk to, the interface segregation principle says break it down. Smaller, more focused interfaces.
Okay, so instead of one giant phone switchboard for a whole skyscraper, you have smaller ones for each department. It seems much more efficient, less room for error.
You got it. That way different parts of your code can interact with just the interfaces they need for their specific job. They don't need to be bogged down by a bunch of extra stuff that's totally irrelevant to them.
So less like tangled spaghetti code and more like a well-organized spice rack where everything has its own little spot. Sounds like this principle keeps things nice and tidy.
Absolutely. Each part of your code is like a chef with their own workstation, and they only need access to the tools and ingredients that make sense for what they're cooking. It makes the code more maintainable, reusable, and less likely to have errors.
This makes me think about those multi-purpose kitchen gadgets, the ones that are supposed to do everything.
Oh yeah, I know those.
They always turn out to be kind of mediocre at everything, and they take up a ton of space.
Exactly. In the same way, it's better to have smaller, specialized interfaces in your code. It's just the cleaner, more streamlined way to work. Because when you need to make a change to one part, it's less likely to affect other unrelated parts of your code.
It's all about clear boundaries and responsibilities, just like a well-organized kitchen. So I'd for interface segregation. Just the right tools for the job.
Perfectly said. Ready to tackle D's in solid, the dependency inversion principle. It can be a little tricky, but it's really important for building flexible, maintainable software.
Bring it on. Let's unravel this dependency inversion thing and see what it's all about. All right, D for dependency inversion. Sounds kind of complicated, like some sort of coding magic trick. What's the deal with this one?
Well, it might sound a bit intimidating at first, but really it's about keeping things flexible and easy to change. Think of it like building a house of cards.
Okay.
If every card is totally dependent on the one below it, the tiniest nudge could make the whole thing collapse.
Right. One wrong move and it's over.
Exactly. We want to build our code so it's way more resilient, less like a house of cards and more like, say, a Lego castle.
I like where you're going with this. So we want our code to be like Lego bricks, like independent and swappable.
Exactly. Each module should be like a Lego brick. And that's where dependency inversion comes in. It's about depending on ideas, abstractions, rather than specific ways of doing things.
Okay, abstractions, I'm with you. But break that down for me a little.
Sure. Let's go back to our banking app. Say you've got a module that sends notifications to users, things like account updates, payment reminders, that sort of thing.
Right.
Now, a concrete implementation would be to write code that sends those notifications directly through email.
Okay, so you'd have all this code about formatting the emails, connecting to the email server, sending it all out.
Right. But what happens if, down the road, you want to start using text messages, SMS, or those push notifications? You'd have to go back and rewrite a bunch of that code to make it work with the new methods.
Yeah, that sounds messy. Every time you want to add a new way to send a notification, you're messing with the existing code, which means more chances to break things.
Totally. That's where dependency inversion swoops in to save the day. Instead of tying our notification module directly to email, we create an abstract interface. Let's call it notifier. This interface, it defines how to send notifications, but it doesn't care how those notifications actually get delivered.
So it's like having one of those universal remotes, the kind that can control any TV no matter the brand.
Exactly.
The remote doesn't need to know the specifics of each TV, it just sends the right signals.
Perfect analogy. So you'd have separate pieces of code for email notifications, SMS notifications, push notifications, all that. Each one would follow the rules of our notifier interface, but they'd each have their own way of actually delivering the message.
I'm seeing it now. Our notification module, it's not directly tied to any one delivery method anymore. It just talks to that notifier interface.
Right. Exactly. It doesn't care if the message goes by email, text message, or carrier pigeon. It just knows to send the message to the right notifier and let it handle the details.
So it's like having a dedicated messaging service inside our app. We just give them the message, they take care of the rest.
Exactly. And if we need to add a new notification method, we just create a new piece of code that follows the notifier interface, and the rest of our code just like rolls with it. No drama.
That is incredibly cool. It's like you future-proofed your code. No matter what new ways of sending messages come out, you're ready.
That's the power of these solid principles. They help us build software that isn't just working today. It can adapt and keep working even as things change in the future.
This has been awesome. Single responsibility, open-closed, Liskov substitution, interface segregation, dependency inversion. Solid. These might seem kind of abstract when you first hear them, but they make such a big difference in how we build software.
Totally. They're the guiding principles that help us go from just lines of code to these robust, scalable, and maintainable systems. And like we've been talking about, they apply no matter what specific programming language you're using. It's a whole philosophy of building elegant and resilient software.
So before we wrap up, what's the one big takeaway you want our listeners to walk away with from this deep dive?
Next time you're using a piece of software and it just works, whether it's an app, a website, some big complex system, remember, there's a good chance these solid principles were part of making that happen. They're like the unsung heroes of software, making sure things run smoothly and adapt to whatever gets thrown at them.
I like that. It's like appreciating the craftsmanship behind like a handmade watch or a perfectly tuned instrument. You might not see the solid principles directly, but they're the foundation of good software.
Exactly. And now our listeners, they have a little peek behind the curtain into the world of the people who build those digital masterpieces, guided by these principles of solid design.
This has been an amazing deep dive into solid. Thanks for joining us. Until next time, may your code be ever solid.